Now, a few days ago, this interesting problem popped up on the internet, which I thought I would have a go at. Einstein here is rowing a boat upstream under a bridge, which knocks off his hat, falls in the river and floats downstream, but he doesn't notice. He carries on. 5 minutes later, he realizes his hat's gone, figures out it must be in the water, so he turns the boat round, and we'll assume that's instantaneous, and rows with an equal effort in pursuit of the hat. He catches it 1 kilometer from the bridge. What was the speed of the river? So the easiest way I found to look at this is to sketch it out and create a distance time graph, distance from bridge against elapsed time. Let's have Einstein's rowing speed in still water as VE. The river drifts at VR. So there's the 5 minutes before he notices the hat's missing. He turns around instantly there and comes back, faster coming back, because you can see the slope there is greater, because he's going with the stream, so it's VE plus VR, whereas before it was VE minus VR. The hat, of course, goes at constant speed or velocity if we interchange vectors and what have you. Not worrying about that. VR goes a constant straight line speed down there, and then 1 kilometer, this is the distance down from the bridge, 1 kilometer from the bridge here downwards, he finds the hat. So he's had 5 minutes of rowing upstream, turns around, and then we'll call it T seconds, or minutes rather, to go till he finds the hat down there. Now the calculation is not particularly difficult. I'm sure there's several ways of doing it, but I employed first of all that distance is velocity times time. So if he has the hat's drifted and been found 1 kilometer downstream from the bridge, the hat drifted at velocity VR, and the total time would have been 5 minutes plus the unknown t. Second, we have got a distance that Einstein has been going upstream, which would be velocity e minus VR times the time 5. Then he turns around and we have the time taken t. He is now going at VE plus VR multiplied by the time. And so the total distance he will do would be, he was X kilometers upstream. He's now got to the bridge, that's X, and he's gone 1 kilometer downstream. So his distance is X plus 1, and we have that equation there. I'm not going to go through every single step. If you take equations 2 and 3, subtract them, then we get this little rigmarole here. But we know equation 1 is telling us that VR is equal to 1 over 5 plus t, just rearranging that. Pop that in to VR, and very nicely it boils down to a simple expression that we have VE into t minus 5 is 0. Now the velocity term can't be 0, otherwise he wouldn't be doing anything. So it must be this t minus 5, which is 0. Therefore t minus 5 is 0, and t equals 5. So if we know that t is another 5 minutes, we have equation 1, pop the t as 5 into that, and therefore we very soon find that VR must be 1 over 10 kilometers per minute, and that seems a reasonable kind of speed for the river to be going. Well, the next thing I looked at, and I was curious, I thought, how fast is Einstein rowing? Let's put the VR term of 1/10 back into the equations and figure out how fast Einstein was going. And I had a little bit of trouble with that, because I kept ending up proving things like 5 minus VE equals 5 minus VE. The left-hand side of the equation and the right-hand side of the equation kept coming up the same, and I had a little bit of a thought. So I then thought, well, maybe it doesn't matter. So I constructed in Excel a small spreadsheet and put the values in for, there we've got Einstein's speed in still water and the river speed of 0.1, and then it obviously sketches things out. Now the distance is flipped here. This is the hat drifting. So if we were to change the river speed to 0.2, then clearly the diagram would change. We won't do that. If we change the time from 5 minutes and made the problem 6 minutes, then we would get that. But I had a little look here. So here we've got 10 minutes elapse. He finds the hat with the speed which we've got there. So as a guess, 0.3 for Einstein, that works out, you get the 10 minutes, and the distance would be 1 kilometer. But if we put in 0.4, so Einstein rose faster, and as I suspected, the time comes out to be exactly the same. 1 kilometer down, and 10 minutes later, there we go. He's obviously gone further upstream, and we had to go further downstream. But even if we made this 10, we give him sort of powerboat speed, 10 kilometers per minute. We get the graph like that. He has now gone 50 kilometers upstream and 51 downstream, but it's still 10 minutes and it's still 1 kilometer, which was really quite an interesting thought. If we made it at stupid numbers, then you wouldn't notice the difference from the time axis. You wouldn't notice that there was much difference. Now, what about if he's going slower at 0.2? 10 minutes, 1 kilometer. What if he was going at very slow speeds? Now what I thought then was, let's just do a slightly different spreadsheet. So I played about a little bit, and then I made a new graph and plotted individual time increments for no particular reason. But this one I added, what is the separation distance between Einstein and his hat? So we would get the green line in this case doing that. The red line is the hat drifting, and Einstein is going along at that particular 0.2. So changing that, 0.4, the distance between Einstein and the hat, the maximum distance goes up, but he gets back to the starting point still in 10 minutes and at 1 kilometer away from the bridge. And I thought, well, what about if he goes at a very slow speed, so 0.02, and we would have this happening. Now everything is drifting downstream. He doesn't get past the bridge at all, so we assume then he was upstream of the bridge, and he was very, very poor rower, and as he went downstream his hat fell into the water and would then run away from him a little bit, and then he turns around and goes after it, and he will still catch it at the crossover point here, which is at 10 minutes. The crossover there is a bit harder to see because there's not much of a difference in slope, but there we go, it works there quite nicely. Now what if he doesn't bother to row? Clearly he is going to drift downstream with the hat, so he could just reach down and pick it up, but of course he's a bit dopey. He doesn't notice it's fallen off after 5 minutes, so then it would be a different time. Obviously he could then say, oops, my hat's fallen in the river, and he could reach down and pick it up. So that could occur at whatever distance he had drifted when he noticed what was happening. So that one, there's a discontinuity. Everything else, so even if he's going at 0.001, the actual crossover point then is at 10. So when he stops, there's a little bit of a discontinuity and it suddenly becomes 5. But then what about if he is going in the opposite direction? What if he's rowing downstream? So what we would have here is the hat falls off and it goes down along the red line there. The Einstein hat separation of this one is going to be along the same line, but now Einstein is going way past it. He's now outstripping the hat. After 5 minutes he thinks, oops, my hat's fallen off. So what he does is he turns around and now rows upstream. Now if he's rowing upstream and the river's coming down at the same rate, he doesn't move at all. So he stays steady at fixed position and waits for the hat to catch up with him. So therefore we have a nice little symmetrical graph. The distance between Einstein and the hat increases to that, and then the hat drifts down to him and away he goes there. But let's make him go even faster, minus 0.2. Now he's cranking it downstream quite rapidly here, and we notice each time it only turns out to be 10 minutes later, and 1 kilometer. Where's the 1 kilometer? There it is. 1 kilometer past the bridge is when he catches the hat. Even at minus 2 we would have this happening, and again 10. The only thing that is going to change the 10 minutes is if we change the time of the upstream exercise or the speed here. So it's quite fun that Einstein invented the theory of relativity, and we've now got quite a good example of relativity because we have to look at his speed. Now on the original website, it was on Twitter where I made a few little comments here, and somebody made a very clever statement that of course it helps if you don't think about the bridge and the river bank and the earth. Let's just think about the water. So if the water was still, if we just imagine a body of water of infinite length, Einstein is rowing along, his hat falls in the water. If he rows for 5 minutes past his hat and then realizes it's fallen off, he obviously has to take 5 minutes to come back again. Doesn't matter how fast he can row at. He can go 5 minutes upstream, oops, where's my hat? Turns around 5 minutes downstream. So relative to the water and the hat, Einstein's speed has got nothing to do with it. It's totally irrelevant. Unless perhaps if he was going at relativistic speeds and time dilation, somebody on the river bank would think he's taken 5 minutes upstream and 5 minutes back down again, but Einstein would think no, I got there much quicker. He would not have aged by 10 minutes. He would have had quite a fun time. Yeah, anyway, there we go. That was just some rambling thoughts on this little puzzle.